Okay, so we're going to do a little bit more on stereochemistry, and in particular what I wanted to talk about this time was some terminology. And I've already started to use these terms, but nevertheless it's worth defining a couple of them explicitly. So a chiral molecule, as I said before, is a molecule that can rotate plane polarized light. Often chiral molecules contain stereogenic centers, but not always. There are in fact molecules that have 4 unique things bound to them, and they can rotate plane polarized light, but they don't contain any one spot on the molecule that's a stereogenic center. An achiral molecule is one that cannot rotate plane polarized light. If a molecule is achiral, then it has a plane of symmetry in it somewhere. You can find a plane of symmetry in it. And this is actually a more useful rule in the other sense. If you can find a plane of symmetry in the molecule, then the molecule is achiral as a whole. So one of the compounds that we've already used for assigning RNS problems was a molecule that looks rather like this. And so the question is this molecule chiral or not? And one easy way to start analyzing a question like that would be to say, all right, does it have any stereogenic centers? Does it have any atoms with 4 unique things bound? And in those previous problems, what we did was decide that these 2 carbons that the bromines are attached to are in fact stereogenic centers. There are 4 unique things bound. There's the bromine itself, there's the hydrogen that's lurking behind in both cases, and then the path toward the bromine and toward the methyl are different from each other. So this is a chiral center and this is a chiral center. This position right here, though, in yellow, is not in fact a chiral center, and that is because you do in fact have a plane of symmetry running down the middle of the molecule. There is symmetry to both sides from here. So in other words, if you start analyzing that particular position, then there's the methyl and there's the H, but then you have symmetry as you go from there. So anyhow, this molecule as a whole then must be achiral. Why? Because it contains a plane of symmetry. Does it have chiral centers? Yes, these 2. Not this one, this is not a chiral center. But it has chiral centers in it, and yet it's achiral overall because it has a plane of symmetry. So we previously talked about enantiomers, which is to say molecules that are nearly identical to each other, but not quite, and the thing that is different about them is that at their stereogenic centers, they are flipped. The way I generated these 2 molecules is by generating the mirror plane of one of them. So this is an enantiomer. They're non-superimposable mirror images. But the other way of thinking about it is that there is a single stereogenic center in each molecule, and they are flipped. And when I showed you on the video the Chem 3D image, you can see that they cannot be superimposed. So they are mirror images, that's the mirror plane, but they cannot be superimposed. And again, that's what an enantiomer is. In order for a molecule to potentially have a diastereomer, you must have at least 2 stereogenic centers, and at least one of those stereogenic centers needs to remain the same between the molecules, and at least one of those stereogenic centers needs to be different. However, that's actually overstating things a little bit. This molecule and this molecule are nearly identical. The only thing that's changed is where this methyl is. This methyl is down relative to the ring itself. This methyl is up on the same side as the bromines. So all I've done is hold these 2 stereogenic centers constant. They have not changed. And the thing that's not actually a stereogenic center has flipped. This molecule, of course, is achiral because it has the plane of symmetry running right smack down the middle, and yet this molecule and this molecule are diastereomers of each other, and that's because the bromines have stayed the same, but the pseudo-stereocenter, the not a stereocenter because of the symmetry, but it could be,
that is properly known as a prochiral center. Not yet chiral, but could be, if you desymmetrized.
That spot has flipped. The relationship between this methyl and this bromine, they are on the same side of the ring as each other. That we call cis. The relationship between this methyl and this bromine, which are on opposite sides of the ring from each other, we call that relationship trans. I've illustrated diastereomers with these 2 molecules so far because I wanted to illustrate one more point, and that is that there are compounds that we call meso that contain at least 2 stereogenic centers and yet are not chiral because they have a plane of symmetry. And these 2 molecules right here are examples of meso compounds. Both of them are achiral, both of them contain a plane of symmetry, and both of them have multiple stereogenic centers, at least 2 stereogenic centers. So, what is a meso compound? It is a compound that has 2 or more stereogenic centers and a plane of symmetry. And meso compounds are achiral because any compound that has a plane of symmetry is achiral. However, I would like to draw another diastereomer here, and that would be one that's related to the original by holding the bromine constant and this methyl constant, and this bromine now I'm going to flip. This too would be a diastereomer of the original compound, but now notice that there is no plane of symmetry. The bromine is up, this bromine is down, the bromines are trans to each other, and what that means is that now we have two stereogenic centers there. Ironically, this methyl spot is still not a stereogenic center, and that is because if you try to assign priorities, you would find that it's still a tie going both directions. But the molecule as a whole no longer has a plane of symmetry. Therefore, this molecule is not a chiral. This molecule is chiral. This one contains no plane of symmetry. It is, of course, a diastereomer of both of these molecules. So it's a diastereomer of that because you've flipped this stereogenic center. It is a diastereomer of that because, again, you flipped that stereogenic center, as well as flipping the methyl. A molecule like this that has two double bonds so that no one carbon in this molecule can be bound to four unique things can nevertheless be a chiral molecule. And that is because if you were to build a model of this, you would find almost immediately that it has a top and a bottom, a left and a right, and because of that, it is a chiral molecule, even though no one spot in it is a chiral center. And molecules that have this sort of property of being chiral without a chiral center, they have axial chirality. There are plenty of examples of axial chirality out there, but almost all of them involve restricted rotation of some kind, or the molecule's frozen in place because of double bonds, something like that. So anyway, there are molecules that exist that contain axial chirality. This molecule has no stereogenic center, but you could generate the enantiomer of it, and if you were to build this with your model kit, you would find that it's relatively straightforward to generate the other enantiomer of it, the mirror image that's not superimposable. So enantiomers are always non-superimposable mirror images, and frequently they have one chiral center, and you flip it, but they don't have to. They could have zero chiral centers, like axial chirality, or they could have many chiral centers. So the key feature for enantiomers is simply they are non-superimposable mirror images, or all stereogenic centers must have flipped. To define axial chirality a bit more precisely for our purposes, we will simply say chiral, but no stereocenter.
There's another crucial point to highlight about the difference between enantiomers and diastereomers, and that is, as I've described before, a pair of enantiomers are identical molecules in all respects other than one rotates plane polarized light in one direction and one in the other, and you can separate them only on the basis of the way they interact with other chiral molecules, but otherwise the properties are identical. The reason why that's important to point out is diastereomers are fundamentally different molecules. If you were to look at any two of these molecules relative to each other, they would have different boiling points, they would have different melting points, they would have totally different NMRs, there would be subtle differences there, they would have different polarities. Diastereomers are fundamentally different molecules. They have different properties on any way that you would measure them. That's not true for enantiomers. Enantiomers, the only difference is they rotate plane polarized light in opposite directions. But diastereomers, again, fundamentally different molecules with totally different properties.
So one last thought I wanted to leave you is we've discussed before how your hands are enantiomers, or the quintessential example of enantiomers, and you can therefore think of each hand as being its own chiral center. Likewise, you can think of your feet as being chiral centers. But human beings, as a rule, are meso, because we have a plane of symmetry running right down the middle of us. And for that matter, then, human beings are achiral overall. So just keep that thought in mind. Your right hand, your left hand, enantiomers with each other. You, as a human, have at least 4 stereogenic centers, and since you have a plane of symmetry nonetheless, you are meso.